For grade 12, in today's lesson we're going to be looking at photoelectric effect. So before we start with the question, I just want us to have a look at this data sheet and formula sheet so that we familiarize ourselves with some of the values here and the formulas, right? So when it comes to photoelectric effect, these are the values that we should keep in mind, right? So not to memorize them, but to know that we are going to use them, right? Then the speed of light in a vacuum, given as the symbol C, is equals to 3.0 times 10 to the exponent of 8 meters per second, right? So this one will come in handy. Then we have the Planck's constant, which is given by the symbol H, is equals to 6.63 times 10 to the exponent of negative 34 joules second. And then we have here the charge on electron. So note the values that we will need to know, right? The charge on electron E is negative 1.6 times 10 to the exponent of negative 19 coulombs. So you will still remember this from our electrostatics. And then the electron mass, which is the mass of the electron, is given as 9.11 times 10 to the exponent of 31 kg, right? Then if you know all this, then you are good to go. Now let's look at what we have here. So we are given the formulas. So we have the formula. Starting from here, we have the formula of the energy of the incident light, or the energy of the photon, which is equals to the Planck's constant multiplied by the frequency of the incident light, right? Or you can break it down to this. So your frequency can be broken down to speed of light over lambda, which is lambda is the wavelength, right? So if you do not have the frequency, you can break down your frequency to this, right? And then the formula that we are going to use is obviously this one here. So this goes E is equals to WO, which is the work function. So this one is work function, and then plus EK max, right? So EK max is just the maximum kinetic energy, right, that will be obtained by the photoelectrons after they have reached an energy that is greater than the work function. So all these terms will be explained as we tackle the question. So this is energy of the photons, right, like that. So now, without any further ado, let's just look at the first question that we have. So we have question 10. It says light is incident on the cathode of a photoelectric cell connected in a battery and a sensitive ammeter as shown below, right? Then 10.1 says what conclusive evidence about the nature of light is provided by the photoelectric effect. Now you will note that when we look at this topic, we first find out that light has a dual nature. So what do we mean by that? We mean that light can appear in the form of a wave, and it can also appear in the form of a particle, right? So now they want us to note which one are we investigating here. What evidence shows us, what conclusive evidence about the nature of light is provided by this photoelectric effect. So in photoelectric effect, we are simply looking at the light in the nature of a particle, right? So it's the particle nature of light. And then we have here the cathode has a work function of 3.42 times 10 to the exponent of negative 19 joules. Then 10.2 says define the term work function, right? So let's quickly run to that. We say work function is the minimum energy of incident photons needed to emit electrons from a metal surface, right? So that's how we define it. And then here we are given that light of frequency 5.92 times 10 to the exponent of 14 hertz is shown onto the cathode. Then 10.3 says calculate the maximum kinetic energy of an electron ejected from the cathode, right? So here we must calculate the maximum energy that is ejected from the cathode. Then to answer that one, we have our formula is E is equals to the work function plus EK max, right? So this is where we get to use the formula now. And then breaking down this one, we have the Planck's constant multiplied by the frequency. Then our work function here, if we read, we can see that our work function is given here on this statement. So it's 3.42 times 10 to the exponent of negative 19. So we have 3.42 times 10 to the exponent of negative 19. And then what is our EK max? This is what we are looking for. So EK max, right? Then let's substitute here. Our Planck's constant is 6.63 times 10 to the exponent of negative 34. And then the frequency that we were given here, we were told that the light has a frequency of 5.96 times 10 to the exponent of 14 hertz. So we substitute it here. 5.96 times 10 to the exponent of 14, and then equals to 3.42 times 10 to the exponent of negative 19 plus EK max, right? Then having to calculate this one, we have 39.5148 times 10 to the exponent of negative 20. So I'm aware that your calculators might not be showing this the way I'm saying it, but then at the end of the day, whatever value that you got, you get here, whether it's 3.9, it's just a matter of the decimal places in here. Then we have minus 3.42 times 10 to the exponent of negative 19 is equals to EK max, right? And then now let's punch that in a calculator. We have EK max will now be equals to 5.31 times 10 to the exponent of negative 20 joules. Okay, so now we have 10.4. It says the ammeter registers a constant current of 0.012 amperes, right? And then it says calculate the minimum number of photons of light that strike the cathode in the 10-second period, right? So what are we supposed to do here? We are also given a 10 seconds period. So what are we supposed to do here? We can see that we are given the current, and then we are also given the time. And here the question is asking us to calculate the minimum number of photons of light that strike the cathode. So now we understand that as the photons strike the what you call the cathode here, electrons will be emitted, right, from this metal surface. And when these electrons are emitted from this metal surface, what happens? There is now current that flows in this circuit, right? Therefore, the ammeter registers a particular reading. This reading is 0.012 amperes. So now we are asked to calculate the number of photons that were actually emitted from this cathode, right, or from this metal surface. So now let's check. How are we going to calculate that? The first thing that we have to do is to make use of this formula here in order to get the charge of the electrons, right? So to calculate that, we will say, okay, now we have I is equals to Q over change in T, right? Now, what is our current? The current that is produced here is 0.012. And then we are looking for the charge. And then what is the time that we are given? 10 seconds. So if we cross multiply this, our Q is now equals to 0.12 coulombs, right? So this is the charge of the photons, or rather the charge of the emitted electrons, right? Then now to calculate the number of photons that were produced, we now need to make use of the formula that goes N is equals to Q over E. So you will remember this formula from grade 10, especially when we were dealing with electrostatics. So this is the formula that we use to calculate the number of electrons. Why are we using this formula? We understand that the number of electrons represents the number of photons that have been produced or emitted, right? Then we have N here, and our Q is 0.12. The E here is known as the charge on the electron, which we discussed earlier. And then in this case, we can see that if we go check it on the or on the data sheet, it appears as a negative. So the E there appears as negative 1.6 times 10 to the exponent of negative 19. But in this case here, because our number has to be an integer, positive integer, to be specific, then we need to substitute it as a positive, because the Q that we have here, the charge is positive. Therefore, in order for us to have a positive integer, this should be a positive divided by a positive, right? So even in grade 10, that's how we did it. Then it's 0.12 over 1.6 times 10 to the exponent of negative 19, which will give us 7.57 times 10 to the exponent of 17, and then electrons, right? Which we know that if we have this number of electrons, that means that the number of photons is also equals to 7.57 times 10 to the exponent of 17. Because what is these photons that we are actually talking about? These are the electrons. These are the charged electrons, right? The electric photons, right? Now, in 10.5, it says the intensity, the intensity. Note that when we say intensity, we are usually increasing the brightness, right? So the brightness of light, or the power of light. The intensity of the incident light is now increased, right? So the brightness or the power is now increased. How will this change affect the reading on the ammeter? How will this change affect the reading on the ammeter? So we do understand that even if we look at it based on this formula here for electricity, if we increase the power, which is the brightness of the bulb or the incident light that has been used, then we will have to obviously, this will obviously increase the current, right? Because power and current, they are directly proportional. But then how do we explain it in terms of this? So it says choose from increases, decreases, or remain the same, and then explain the answer. So we already have the solution, it's increases. But then how do we then explain? We say increasing the intensity of light increases the number of photons emitted per unit time. So when you are increasing the intensity of light, that means more photons will now be emitted from the metal surface, right? So there'll be more electrons emitted on the metal surface as compared to when you have a low intensity light. So increasing the intensity of light increases the number of photons emitted per unit time, or per second in case of the current, because remember it's the charge over change in time, which the change in time is in seconds. So thus resulting in an increase in current, right? So remember, if we are increasing the number of photons that are emitted, this will increase the charge, right? So the charge will now increase because there will be more number of photons passing through a point per given second, right? So if the charge increases, then what happens? The current also increases. Okay, so we have yet another question. It says a photoelectric cell is connected in a circuit. The lowest frequency of light that will emit electrons from its calcium surface is 5.1 times 10 to the exponent of 14 hertz. Let's look at what they're saying here. The lowest frequency of light that will emit electrons. The lowest frequency of light that will emit electrons. Let's go read 10.1. 10.1 says define the threshold frequency. Can you see that the examiner here already gave you the definition of the threshold frequency, right? So we are supposed to say threshold frequency is the minimum frequency of light needed to emit electrons from a metal surface. Then 10.2 says calculate the work function of calcium for 3 marks, right? So we can see that here, what are we given? We are given the threshold frequency, which can be written as FO. So that's 5.1 times 10 to the exponent of 14 hertz, right? And then what are we looking for? We are looking for the work function, which is written like that. So I don't know what they call it. Then that's the work function, right? Then how are we going to be able to calculate the work function? We know that the formula to calculate the work function is just WO, and then we have HFO. Then remember, H here is what we know as the Planck's constant. So you just simply substitute that value in there. So our Planck's constant is 6.63 times 10 to the exponent of negative 34. So remember, you don't have to memorize any of these values. This will be given. All constants will be given, right? Then 5.1 times 10 to the exponent of 14. Remember, this one is the one that we are given, the threshold frequency. Then obviously for a 3-mark question, we know that it's a formula, substitution into the formula, and then the correct answer. So we have 3.38 times 10 to the exponent of negative 19 joules, right? And just like that, you have your 3 marks. Easy peasy. Then 10.2.2 says, calculate the amount of energy carried by the incident photons of violet light. Calculate the amount of energy carried by what? By the incident photons, right? So remember, when they say the energy of photons, this is what we refer to. Remember, in our formula, E is equals to work function plus EK max. All these are energies, right? So work function is the minimum energy needed to emit electrons from a metal surface. But this E here is energy of a photon, and this EK max here is the energy, the kinetic energy of a photon after it is emitted from the metal surface. So this is the energy, the kinetic energy. This is the energy that it will be able to move with. Remember, kinetic comes from the word kinesis, which means movement, right? Right. Then it says, calculate the amount of energy carried by the incident photons of violet light. So right now, the energy that they're looking for is this one, the energy of the photon. So what are we supposed to do here? We can simply just write E is equals to HF, but then you can see that here we are not given anything on the frequency of the photon. So what are we supposed to do now? We break down this frequency, and then we say 1 over. So we are not given the frequency of the incident light, meant to say. So this can be broken down as C over lambda. So this is what we're going to substitute here. E is equals to H, and then we have C over lambda like that. And then we can substitute in our Planck's constant, which is 6.63 times 10. You can find it in your data sheet. And then negative 34. And then C is the speed of light in vacuum. So 3 times 10 to the exponent of 8 over, remember, we've been given the wavelength. The wavelength was given as 400 nanometers, which we said this will be 400 times 10 to the exponent of negative 9 meters. So let's substitute it here. So we have 400 times 10 to the exponent of negative 9, right? So when you punch all this in your calculator, the answer that you'll get for this one is 4.97 times 10 to the exponent of negative 19 joules, right? So this is the energy of the incident photons. Then 10.2.3 says, calculate the maximum. Now they want the maximum kinetic energy of the photoelectrons. So note now they're saying of the photoelectrons because they will be now emitted from the metal surface, and now they'll be flowing in the circuit. So they're now photoelectrons emitted from the calcium surface when the violet light shines on it. So we know when it comes to that, we now have to make use of this formula. So it's E is equals to the work function plus the EK max, right? Then what is the energy of the photon? Remember, we calculated from previously, and then we got 4.97 times 10 to the exponent of negative 19, right? But then what is the work function? Also, the work function, we calculated it in 10.2.1, so we can just substitute it in. So this is 3.38. So you see that these are follow-up questions. So you have to be very careful with these questions, guys, because one mistake, you might forfeit a lot of marks, right? So remember, I always tell you that do not count upon positive marking. Write the correct values. Then here, obviously, you have to take this one, transpose it to that other side, and then when you subtract, so yeah, you can just subtract there. No need to write that step. So 4.97 times 10 to the exponent of negative 19 minus all of this. This will give us 1.59 times 10 to the exponent of negative 19 joules, right? And just like that, you have your EK max. Okay, so let's look at another question. It says an experiment is conducted to investigate the relationship between the frequency of light incident on a metal and the maximum kinetic energy of the emitted electrons from the surface of the metal. This experiment is conducted for 3 different metals. So we have potassium, zinc, and platinum. Right, then 10.1 says name the phenomenon on which the experiment is based. So it is based on what we are actually doing here, which is called the photoelectric effect, right? Then 10.2 says name the physical quantity represented by X on the graph. Now you will note that whenever we are given a maximum kinetic energy versus frequency graph, what we have here on the y-intercept represents what we know as the work function, right? So this is the minimum energy required or needed for in order to emit electrons from a metal surface, right? So this is the work function. Always note that the y-intercept will represent the work function, right? And then what about the x-intercept? So they do not ask it here, but then for interest's sake, what does the x-intercept represent? The x-intercept actually represents, because here we can see that we have frequency, the x-intercept will be representing the threshold frequency, so which is the minimum frequency needed to emit electrons from a metal surface. So y-intercept is work function and x-intercept is your what you call your threshold frequency. But then note, sometimes they can inverse the graph, right? So by that, I'm saying they can sometimes put maximum kinetic energy here. So maybe put kinetic energy here and they decide to put frequency up there, right? So that is also possible. Remember, they can do whatever with the graphs, right? You just have to know that if your frequency is here, then this value here will now be representing the threshold frequency, and the value in here will now be representing the work function. Not so easy to not so hard to spot. Then now name the physical quantity. We already did that. It's the work function, right? Then 10.3 says which one of the 3 metals needs incident light with the largest wavelength, right? With the largest wavelength. Now we can see that we are not given anything on wavelength here, but then we can answer this question on wavelength based on the relationship that we know on wavelength and frequency. So we know that frequency is inversely proportional to wavelength. So the one that will require a greater wavelength is the one that will obviously have a lower frequency. But what lower frequency? A lower threshold frequency. So which one between these three metals has a lower threshold frequency? Remember I said the x-intercept here, the x-intercept, pardon me, are representing our threshold frequencies. So it goes without saying that potassium here is the one with the lowest threshold frequency and therefore will require light with the largest wavelength. So the answer to that one is potassium. Then 10.4 says define the term work function, right? So what is this work function I've been talking about? So work function is the minimum energy of an incident photon needed to emit electrons from a metal surface. Or you can just write any other simple definition that you know. So in layman's term, work function is just the minimum energy needed for electrons to be ejected or to be moved from a metal surface. Then 10.5 says calculate the work function of platinum. So we must calculate the work function of platinum, which is WO. Then where is platinum? From platinum we can see that here we are given the threshold frequency, right? So if we can just find the average between these two frequencies, then we can know what is the threshold frequency there. So if you say 1.5 plus 2.0 over 2, that will obviously give you what is the threshold frequency. So that will be 1.75. But then be careful here, they gave you that it's not just 1.75, you need to also include this. So times 10 to the exponent of 15. So note when they give you the graph and they put your values in here, right? So that means whatever solution you'll get, you will now then have to express it in the form of 10 times 10 to the exponent of 15, right? Okay, so now let's calculate the work function. So for 3 marks, we know what formula to use when we are only given 3 marks. It's just simply H times the threshold frequency. So the H is the Planck's constant. Then what is that? Planck's constant is equal to 6.63 times 10 to the exponent of negative 34. And then our threshold frequency, remember it is just the average between those two. So it's 1.75 because we can see that it is actually the midpoint of the 1.5 and the 2.0, right? So that's 1.75 times 10 to the exponent of 15, right? So be careful. And then multiplying that, of course, it gives us 1.16 times 10 to the exponent of negative 18 joules, right? So then for 3 marks, formula substitution, correct answer. So let's look at 10.5.2. It says calculate the frequency of the incident light that will emit electrons from the surface of potassium with a maximum velocity of 5.60 times 10 to the exponent of 5 meters per second, right? So okay, having to calculate that one, let's see now. We have our formula is equals to E, and then we have the work function plus EK max, right? And then the frequency that we are trying to calculate here is the frequency of the incident light, which we know will be this one, right? So if we break down the E here, this is H times F, the frequency that we are looking for. But then you will remember that from 10.5.1 we had already calculated the work function, right? So we have 1.16 times 10 to the exponent of negative 18. And then now what is our EK? So EK is half, and then this is the mass of the electron, so and V squared, right? So we are given here that the velocity is 5.60 times 10 to the exponent of 5. So we're just going to substitute. Let's first substitute our Planck's constant, which is 6.63 times 10 to the exponent of negative 34. And then we have the frequency here. substitute our work function like that, and then let's substitute here. So what is the mass of the electron? Remember, we read it from the data sheet to be 9.11 times 10 to the exponent of negative 31. And then here our velocity we've been given as 5.60 times 10 to the exponent of 5. So remember to square that. And then having to calculate now, if you just do the math for all this, so you add all of this and then divide by this number. So let's do it like this so that I can just punch everything in a calculator. So all of this added together, then you divide by this 6.63 times 10 to the exponent of negative 34. Then if you punch all that in your calculator, you get that your frequency is 1.97 times 10 to the exponent of 15 hertz, right? And that's the frequency of the incident light that will emit the electrons from the metal surface. So we are given question 10. It says the relationship between frequency F and maximum kinetic energy of photoelectrons emitted from two cathodes M and N of different photoelectric cells are investigated. Then the graphs below have been obtained from the results, right? So we have M and N here. And then 10.1 says define the term threshold frequency. So quickly, threshold frequency is the minimum frequency of light needed to emit electrons from a metal surface, right? Then 10.2 says how does the maximum kinetic energy of photoelectrons emitted from cathode N compare to the maximum kinetic energy of those emitted from cathode M when light of a frequency greater than 10.40 times 10 to the exponent of 14 hertz is shown on each of the cathodes, right? Now before we can answer that, they say choose from greater than, smaller than, or equal to. So before we can answer that, I just want us to see something here. We can say that we are given an inverse graph, right, of what we usually have. What we usually have is EK max versus frequency, right? So now what did they do? They inversed the graph, right, to give us a frequency versus EK max. Now remember, I told you that in the original graph here, if we have the y-intercept here, this y-intercept is giving us the work function. But if they decide to inverse the graph, the y-intercept here is no longer giving us the work function, but it is giving us the threshold frequency, right? So now we are given the threshold frequency. That means answering this question, we have to refer to the threshold frequencies that we are given here. So now we want to compare. We want to know which one is a greater maximum energy here between M and N. So to answer that, we will say now we can see that with cathode N, the threshold frequency is lower. So we only have 5.16 times 10 to the exponent of 14 hertz. Contrary to 10.40 times 10 to the exponent of 14 hertz, right? So we can see that this one is greater. It has a greater threshold frequency. Now we know that if we make use of the formula E is equals to work function plus EK max, we do understand that here the work function and the EK max are inversely proportional. What do I mean by that? If a metal has a greater work function, meaning more energy, there is a greater energy that is needed to emit electrons from the metal surface. That means the electrons emitted from that cathode or from that metal surface will have a lower EK max, right? Why? Because all the energy will be wasted in trying to make these electrons to at least move, right? So the requirements for the electrons to move or to actually be lifted is way higher, right? And then resulting in a lower EK max. But if the work function is lower, meaning if the requirements are low, right, then that means electrons emitted from that cathode or from that metal surface will have a higher EK max. Right. Now, remember, I'm just speaking about the work function here, but then I'm given the threshold frequency. Now, how do I relate this work function to the threshold frequency? You will understand that work function is actually the Planck's constant multiplied by the threshold frequency. So we can say that the work function is directly proportional to the threshold frequency. So the one with the higher threshold frequency will have a higher work function, then resulting in a lower EK max. But the one with actually a lower threshold frequency will have a lower work function, resulting in a greater EK max. So this is the relationship that we have here. So if we have a lower work function, then we have a higher EK max. Now comparing this to cathode M and N, which one will have a lower work function? We can see that the lower work function will be obtained for cathode N because of a lower threshold frequency, right? So this threshold frequency will result in a lower work function and therefore will result in a greater EK max for a constant energy of photons, right? Then that's how we are supposed to explain that, but then they did not tell us to explain. So the answer here is just greater than. Then 10.3 says calculate the value of frequency f indicated on the graph, frequency fx indicated on the graph. So we can see that we are given this frequency here, and then we can make use of this, right? Let's make use of cathode M, since we can see that it intersects here with M and then all the way there. So we can make use of these values, right? So okay, answering that one, we obviously need our formula. E is equals to the work function plus EK max, right? Then this one, we know that it will break down to HF, so the Planck's constant multiplied by the frequency. Then we have our work function here, which will be H. Remember, we are not given the work function, but we are given the threshold frequency, then plus EK max, right? So what are we looking for here? We are looking for this F there. So let's start substituting. We have our Planck's constant here is 6.63 times 10 to the exponent of negative 34, and then the frequency that we are looking for is this one, right? So remember, that's not the threshold frequency, so let's label it fx, and then here again we have 6.63 times 10 to the exponent of negative 34, and then what is our work function? Our threshold frequency, meant to say our threshold frequency. Let's go back here. You can see that our threshold frequency for M is 10.40, but then we need to take this one also, so it's 10.40 times 10 to the exponent of 14, and then plus the EK max, which the EK max here, we can see that we are given, it reads here 23.01 times 10 to the exponent of negative 19. So it's 23.01 times 10 to the exponent of negative 19, right? And then what are we supposed to do now is just dividing both sides by this 6.63 times 10 to the exponent of negative 34, and then even here 6.63 times 10 to the exponent of negative 34. So you will just have to add all this and then divide by that number. So fx is now equals to 4.51 times 10 to the exponent of 15 hertz, right? And there you go. Okay, so we have 10.4, it says the experiment is now repeated for cathode M using light of frequency fx but of higher intensity, So remember, we said intensity relates to the brightness or the power of the light, right? Then how will each of the following be affected? They say choose from increases, decreases, or no effect. Then 10.4.1 says how will the y-intercept be affected? Remember, we said that the y-intercept in this graph is actually indicating the threshold frequency, right? So what will happen to the threshold frequency of the light if we use a light of higher intensity? You will note that intensity does not have any effect on the threshold frequency, right? Because we are still using light of the same type, right? So for 10.4.1 we say no effect. We are still using the same light, right? So the intensity does not affect the frequency. 10.4.2 says the number of photoelectrons emitted per unit time. So obviously when it comes to that, the number of photoelectrons emitted per unit time will have to increase. So it increases. Why? Because now when you are shining a light of a greater intensity, you are actually causing the electrons to be emitted in a larger number per unit time, right? Thus resulting in a greater current, right? So here it increases. Then 10.4.3 says the maximum kinetic energy of the emitted photoelectrons, right? So if we answered in 10.4.1 that there is no effect, you will know that frequency is directly proportional to the energy, right? So frequency is directly proportional to the energy. So if the frequency remains the same, or rather if the threshold frequency remains the same, that means also the energy will remain the same, right? So remember, the maximum kinetic energy of the emitted photoelectrons, so they will still remain the same. So there is no effect, right? There is no effect because we are not doing anything to the threshold frequency, right? And therefore there will be nothing done to the EK max.